So we have selected different paths to find the work done. Here, body is taken directly upwards. In that case, work done is equal to force into displacement, mg into h. Another path is selected inclined plane. Here, the work done is force into displacement itself, but how much force we have to apply? Mg sin theta we have to apply in the upward direction, because mg sin theta is the component of weight acting along the inclined plane downwards. So we have to apply a force upwards opposite to mg sin theta. Then only it can be moved along the inclined plane. So mg sin theta into Cb you have to calculate. That is calculated here, mg sin theta into Cb, and sin theta is AB by CB into CB. CB get cancelled, we get mg into h, because AB is equal to h. So mgh. And along this path, one step, to take it along this one step, work done is calculated. Mg h dash cos 0. Why cos 0? Force exerted upwards, displacement is upwards, so theta will be 0. So mg h dash cos 0. Then through this horizontal distance, what is the work done? Mg x cos 90. How you got 90? We are applying force upwards, but displacement is along the horizontal direction. So mg x cos 90 it will be. So there are such n steps are there. This is for one step. We have calculated this for one step. There are n steps. So into n you have to take, into n. So n into mg h dash cos 0 is 1. So mg h dash plus cos 90 is 0. So that term vanish. That will not be there. So that will take as 0. So we get n into mg h dash. What is n into h dash? N steps are there. See, h dash plus h dash plus h dash plus h dash plus h dash, like that we are adding. N steps are there. So n into h dash will give what? The total height. N into h dash will give the total height. So we can write n into h dash is total height. So mg into h, we get work done is calculated as mgh. So from this, what you can conclude? To take a body from one position to the other, the vertical height is same. You can adopt a different path. You can select different path, whether inclined plane, whether staircase, whether it is directly upwards. You can take any path, but the work done to take the body from one position to the other depends only on the initial and final positions, not on the nature of the path selected. And such a force is known as conservative force. Here, we are doing this work against the gravitational force. So, gravitational force is a conservative force. Electrostatic force is a conservative force. So, how will you define conservative force? So, you can see the definition here. A force is said to be conservative if work done by or against the force. Now we have taken the example of against the force. Work done by force also is applicable. So force is said to be conservative if work done by or against the force in moving a body depends only on the initial and final positions of the body and not on the nature of the path followed between the initial and final position. So we have seen it here. The work done to take the body from one position to another do not depend upon the nature of the path selected. It depends only on the initial and final positions of the body. Such a force that is known as a conservative force. So what we have proved here, gravitational force is a conservative force. Work done to take the body from one position to the other do not depend upon the nature of the path followed. It depends only on the initial and final positions of the body. So I think you understood. If you have doubt, you can call me after the class. Okay, such a force is conservative force. Example, gravitational force and the electrostatic force. Yes. Work done by or against the conservative force in moving a body through any round trip is always zero. That is another property of conservative force. Conservative force, another property. One property we have studied. Another property is this. Work done by or against a conservative force in moving a body through any round trip is zero. For example, in the above example itself, work done to take the body from A to B. Suppose we are taking that as WAB. You can see in the case of gravitational force, if we take work done in moving the body from A to B against the gravity, if we are taking negative, work done to move the body from B to A, we have to take positive. Any one you take positive, otherwise opposite will be negative. So if we, in this example it is given, work done to take the body from A to B against gravity is taken negative, then you see where is the, do we need to do any work? I'll show the figure. Okay. Net is weak. I will change the net. Okay. So work done to take the body from A to B, if it is taken negative, against gravity, if we take negative, work done to take the body from B to A, that means returning. For example, we are doing so much work to lift the body and to keep it at a height. We are doing. Suppose we are, that work is taken negative. Then you just leave the body after reaching to that particular height, just leave the body. Do we need to do any work? No, it will fall downwards. Isn't it? So work done to take the body to the height x, if we take that as negative, then work done by gravity, that we have to take as positive. Work done. Against gravity, if we take negative, work done by gravity, we have to take positive. So total, what is the total work done? Total work done will be zero. So that is another property of gravitational force. See, work done to take the body from A to B is taken positive. Then work done to take the body from B to A is negative. Then the total work done, WAB plus WBA equal to zero. This is another property of a conservative force. Then next is non-conservative force. A force is said to be non-conservative if work done by or against the force in moving the body from one position to another depends on the path followed between these two positions. So, conservative force do not depend upon the nature of the path, but non-conservative force work done depends upon the nature of the path. For example, frictional force. Suppose we are calculating the work done against friction. To move the body from A to B, there is frictional force, and from B to A also there will be frictional force. So, if the path is longer, frictional force will be more. If the path is shorter, frictional force will be less. It depends upon nature of the path, whether it is rough, whether it is smooth. Depends upon the nature of the path. So, frictional force, you can see, it depends upon the nature of the path. Whether it is rough, whether which material is used, whether it is wood, whether it is concrete, like that. Frictional force depends on work done against the frictional force. It depends on the nature of the path. Understood? So it is a non-conservative force. Frictional force is a non-conservative work done to take the body from one position to other. Depends upon the nature of the path followed. Understand? So a force is said to be non-conservative if work done by or against the force in moving a body from one position to another depends on the path followed between these two positions. Such a force is said to be friction, that non-conservative force. I think you understood conservative and non-conservative. Work done depends upon the nature of the path. Which force is that? Which force is that? Nana? Work done depends upon nature of the path. Nature of the path. Nana is there? Nana? No answer. Pavitra? No, why you are not answering? Pavitra? Vibhansha? Nobody is answering. Gautam, are you there? Gautam? Okay. And I will tell no need to do. Anybody, can you tell? Work done depends upon nature of the path. What force is that? Conservative or non-conservative? Anyone can answer.
Non-conservative.
Non-conservative. Correct answer. Work done do not depend upon nature of the path. Anyone?
Conservative.
Conservative. Correct. Okay, the next. Potential we have. Next. So we have studied two types of potential energy: gravitational potential energy and elastic potential energy. There are two types of potential energy. Have you studied? Yes. I think I have told that. Types of potential energy: gravitational potential energy, elastic potential energy. Gravitational potential energy is just we have calculated work done to lift the body to a height h, mg into h, that is equal to mgh. We have calculated work done to lift the body to a height h, that is what we have calculated, that is for gravitational potential energy. Next is elastic potential energy, that is what we want to derive. That is very important derivation. Net is very not moving. Net is very slow. Okay. Next is elastic potential energy of a spring. That is the derivation that we have to study today. For that, you can see the figure. Elastic potential energy of a spring. You can see a spring here. So here it is fixed at O. One end of the spring is fixed at O. Fixed. Other end, a mass is attached. A small mass is attached at the other end. And this is the original position. It is kept on a horizontal surface. Kept on a horizontal, smooth surface, frictionless surface. So 5 minutes only more. Then, suppose we are stretching the spring to a distance x. We are stretching the spring to a distance x. And you know, when the spring is stretched, a force will comes into play which will bring it back to the main position. Do you know which force bring it back to the mean position? Anyone? When we stretch the spring, a force will be acting to bring it to the mean position. What is the name of the force? Anyone? Anyone? No answer? Which force?
Spring force ആണോ മാം?
Spring force. Yes, that is also known as a restoring force. Okay, correct. Good. So, force will always, when we stretch the spring to a distance x, a force will always, spring will exert a force. That is known as restoring force, which will always try to bring it to the mean position. Mean position is A. And when we compress the spring, then also spring force act. That means that restoring force will come into play to bring into the original position. Whether it is stretched or it is compressed, in both the cases, restoring force will comes into play, which will bring the spring back to the normal position. See, when it is compressed and released, that retain or regain its original position. It is because of this restoring force. So, when it is stretched more, what happens? Restoring force also will be more. So, when it is stretched again and again more, what happens? This restoring force also is increasing. Restoring force also is increasing. But there is a limit for that. When we exceed the limit, we are able to stretch it. We are able to stretch it then when we exceed this restoring force. Understand? So, restoring force is directly proportional to stretch or compression. Restoring force is written as minus of F. Why? Because when we stretch it, suppose towards the right, we are stretching it, restoring force is acting towards left. When it is compressed, we are exerting a force towards left. But you know, the restoring force is to the right to bring it to the mean position. So, whether it is stretched or compressed, both the cases, the restoring force is acting towards the mean position. It is opposite to the displacement. So, we write the restoring force as minus F. So, minus F is directly proportional to this stretch or compression. So, we can write the equation minus F is proportional to x. What is x here? Stretch or compression. So, minus F is equal to, when it is equated, we are multiplying with a constant K, where K is the spring constant of the spring constant or force constant of the spring. What this negative sign shows? Negative sign shows that the restoring force is directed towards the equilibrium position or mean position. So, when we plot a graph between the restoring force and this stretch or compression, we get a straight line graph because they are found to be directly proportional. As the stretch increases, restoring force also increases. We get a straight line graph which shows that F is proportional to x. Then, in order to define the spring constant, K is known as spring constant of the spring. So, F equal to Kx. When x equal to 1, what we get? F equal to minus K or K equal to minus F we are getting. So, x means stretch or compression. So, if that stretch or compression is made 1 unity, what is the force required to stretch it? That will be the force constant. So, force constant of a spring is numerically equal to the force required to produce unit displacement in the spring.